In this video, I'm going to go through OCR A-level Chemistry. This is the 2019 papers, and this is paper 1. I'll just do the first half of the paper in this video and finish the second half in a later one. Okay, so first of all, we have the multiple choice section. And the diagrams below, each represents an orbital. Each box represents an orbital, and each electron is shown as an arrow. Well, we've got to show the correct diagram for carbon. Carbon, atomic number 6, of course. So that's going to be 1s2, 2s2, 2p6. Sorry, 2p2. And so, right, so it's not A, it's not B. Now, which one is it, C or D? Well, of course, this is the correct one because the orbital, the electrons here are not occupying the same 2p orbital. They won't occupy the same 2p orbital, and so they've got to pair up. So this is, this is the correct way here with the two electrons in separate p orbitals. D is the answer there. Right. 2. Which statement about the halogen halide ions is correct? Right, now the halogens are oxidizing agents, okay, not the halides. So they're all oxidizing agents because they have some tendency to accept electrons, okay, so they get reduced themselves. So we can immediately rule out C and D because the halide ions aren't oxidizers, they're actually reducers, they give away electrons. Now, iodine cannot oxidize the bromide ion, of course, because if you look at the reactivity, you've got fluorine, chlorine, bromine, and iodine. They get more reactive as you go down the group. Sorry, less reactive as you go down the group. So chlorine can reduce the bromide ions because chlorine has got a quite a strong affinity for electrons and remove the electrons from the bromides. Iodine can't do that because it's not as reactive. Okay, question 3. One molecule of a gas has a mass of this many grams. Okay, what's the possible formula of gas? Well, we have to work out the MR of the gas, don't we, or the molecular weight of the gas. So the MR is the mass of 1 mole. Here we've got the mass of 1 molecule, so we have to times that by the Avogadro constant, okay, to give us the mass of 1 mole. And if you do that, that is equal to 16.0 or something. Okay, so the molecular mass is 16, and methane has got an MR of 16. O2, of course, is 32, and the others are much bigger. So A is the answer there. Okay, question 4. All right. Laboratory spills can be made safe by adding sodium carbonate, okay, over the acid, and the acid is hydrochloric acid. So just to show you we need to know the ratio in which they react. So you've got sodium carbonate and HCl. You need to know this equation. Right, you're going to get sodium chloride, CO2 and water. And of course, that means you're going to need 2 moles of hydrochloric acid for every 1 mole of sodium carbonate. So what's the minimum mass of sodium carbonate can neutralize that acid? Well, we need to work out the moles of acid there. So let's do that. Moles of HCl, conc times volume, 2 multiplied by 50 over 1,000, the volume in dm cubed, of course. That gives us 0.1 mole. So how many moles of sodium carbonate can that react with? So that's going to be half of that. So the moles of sodium carbonate is going to be 0.1 over 2 is equal to 0.05. What mass of sodium carbonate is that then? Mass sodium carbonate is equal to moles times the MR. So that's 0.1, and the MR of sodium carbonate is 106. So that gives us 5.3 grams. That is the right answer there. Okay. Right. Okay, the oxidation of magnesium in this magnesium compound. Well, magnesium is in group 2, so it always exists as the Mg2+ ion in all of its compounds. So it doesn't matter what it's in. We just have to say, right, it's going to be +2. It's always, magnesium always has an oxidation number of +2 in its compounds. Okay, which reaction is a redox reaction? So we're looking, number 6, we're going to look for something where the oxidation number changes. Okay, now we can rule out, and you can check it, but rule out, this one is a precipitation reaction. There's no exchange of electrons going on there. You don't need to worry about working out the oxidation numbers. You get silver chloride precipitate. B is an acid-base reaction, I think. So yeah, there's no change in oxidation numbers there. If you check everything, the nitrogen, you might think, well, still, and it's the NO2- ion there. It's the NO2- ion there. Hasn't gained or accepted electrons. C is also an acid-base reaction. So we've got calcium sulfate. Yeah, there's no change of oxidation number there. This one, D, you should recognize pretty quickly that the oxidation number of copper there has got to be 0 because it's an uncombined element, whereas the oxidation of copper in copper oxide, well, oxygen is always -2, so copper's got to be +2 there, so the copper has been reduced. Incidentally, what's it being reduced by? Well, the nitrogen is going to have an oxidation number of 0 there, uncombined element. Nitrogen here is -3. Okay, so it's actually been reduced by the nitrogen. Okay. Right. Okay. Which set of elements, number 7, in the solid state contain a simple molecular lattice? Okay, so that's small molecules, a giant covalent lattice, and a metallic lattice. Right. So we need a metal in there. Right. So we can rule out B, C, because there's no metal in there. Let's have a look at A. Well, it's got sulfur. Yeah, that exists as S8 molecules. So that's the simple molecular lattice. So that's what that will be. And silicon is like diamond. That's the giant covalent lattice. Okay. So A is the right answer there. A is the answer. There's no giant covalent lattice in that one. You've got magnesium is the metallic lattice. Phosphorus and sulfur are both small molecules. They're both simple molecular lattice. Okay, question 8. Right. We've got this many grams of a group 2 metal is reacted with an excess of chlorine. We've got that much. We've got that much chloride formed, so we can work out the mass of chlorine in that. So let's do that. So the mass of chlorine and the chloride, just by subtraction, is going to be 9.775 minus 3.528, which is equal to 6.247. Right, now we want to work out, right, so what's important here that it's a group 2 metal. So this chloride is going to have the formula, because it's group 2, it's going to be MCl2, where M is the metal. Right, so we can work out now the moles of chlorine here. Then we can work out, we halve it to get the moles of M. We know the mass of M, so we should be able to work out the atomic mass of M. So let's do that. The moles of chlorine is going to be equal to mass over AR, I should say. 35.5 for chlorine. That gives us the number of moles of chlorine we've got there is 0.176. So we can say the moles of the metal is going to be half that. 0.176 over 2, which is equal to 0.0879. 0.088, we'll say, so it rounds up. Okay, now we know the moles of M and we know the mass of M, we can work out the AR. So AR of M is equal to the mass divided by the moles. Okay, the mass we've got is 3.528. The moles is 0.088. That works out to be 40. So look in your periodic table, which group 2 metal has an AR of 40? It is calcium. Right, which statement is not true for group 2 hydroxide? Magnesium hydroxide can be used to treat indigestion. That's true because it will neutralize acid in the stomach. Calcium hydroxide can be used to neutralize alkaline soils, and that's wrong. It is used to neutralize acidic soils because calcium hydroxide is an alkali itself. So that one is wrong. Okay, so B is the answer there. Let's just check that though. The anion in strontium hydroxide contains an electrons. Well, the anion is OH minus, right? Oxygen has got atomic number 8, so it's got 8 of its own electrons. Hydrogen has got 1 electron, and you've got this extra one here, so that is 8 plus 1, that's equal to 10 electrons. That's true. Barium hydroxide is a product from the reaction of barium and water. That, of course, is true. So B is the wrong answer there. Okay. Radical reactions are responsible for the breakdown of the ozone layer, and the overall equation is shown below. The molar gas volume in the ozone layer is approximately 2.5 meters cubed. Right, it's quite a lot more than our usual 24 dm cubed, and that's because the pressure is much higher and much lower, sorry, in the ozone layer. Right, so how are we going to do this then? What's the energy released in kilojoules in the breakdown of 1 meter cubed of ozone? Right, so moles of ozone in 1 meter cubed is equal to the volume over the molar volume, which is 1 over 2.5, sorry. And that is equal to 0.4 moles of O3. Okay, right now, so we've got 0.4 moles of O3. Now, when we break down 2 moles of O3, we get that many kilojoules. So when we break down 1 mole of O3, we're going to get 284 over 2, which is equal to 142 kilojoules out. But we're not breaking down 1 mole, we're making down 0.4 moles. So how much energy do we get there? Well, we would do, so the energy is going to be equal to the amount for 1 mole, 142, multiplied by the number of moles we've got, 0.4, and that gives us 142, that gives us 56.8 kilojoules out. So A is the correct answer there. You have to be a little bit careful there because this is the value for 2 moles of ozone, not 1 mole of ozone. Right, a question about the Arrhenius equation now. Right, a graph of ln K against 1 over T for a reaction has a gradient of that much. Okay, well we have to remember what is the Arrhenius equation. It's ln K is equal to a constant, ln A, minus EA over R 1 over T. So that means if we plot that against that, that means the gradient or the intercept is ln A. We're not interested in that, but the gradient is going to be equal to that minus EA over R. Okay, so M is equal to minus EA over R. R is the gas constant. Right, so let's rearrange that to get EA. EA is equal to minus M times R. Now we have to be really careful here because R is measured in units of 8.31 joules per mole per Kelvin. It's not kilojoules, so that means our answer for EA is going to be in joules. So let's put the numbers in. The numerical value of the gradient is that, so it's minus 4420 multiplied by it's minus that, yeah, this is the minus gradient, multiplied by 8.31. That gives us a value. So those two minuses give us a plus. It gives us 36,730 joules, which is 36.7 kilojoules per mole. Okay, so that is that, and it's a positive value. The activation is positive because you've got those two negative signs which make a positive, but also activation energy has got to be positive. It's always positive. All right, so C is the answer there. Okay. Right. The dissociation of this acid here in water. Right. What's the definition of an acid-base conjugate pair? Is that you can interchange two species, but you can interconvert, sorry, by addition or removal of a single proton. Okay, so right, we're going to look. So that's obviously wrong because they're not related to each other. That's wrong. Okay, that's wrong. Okay, this is the correct answer because you can turn that into that by losing a proton, and you can turn water back into the H3O by adding a proton. So D is the correct answer there. Those are the three things you can't interchange. They're not acid-base conjugate pairs. Right, this is a tricky question. The number of stereoisomers that this nickel complex can form. Right, now this is a bidentate ligand, okay, diaminoethane, and the chloride ions are monodentate ligands. So we have got this has got a coordination number, this complex, of 6. Coordination, of course, is the number of dated bonds. Okay, so it's going to be, the basic shape is going to be octahedral. So let's draw that. So we've got one ligand sticking up and one down. Okay, so these two wedges coming towards you, the dotted lines going away. Now the two stereoisomers, let's think two obvious ones we can have. We could have the chlorines, first of all, opposite each other. That's one. Or we could have the chlorines, I'll draw this down here, not opposite each other. That would be called the sort of the cis isomer. Okay, so let's have the chlorines, let's say one chlorine there and one chlorine there. Okay, now it wouldn't matter if I put those chlorines like there, those green ones there, it's the same thing. When you turn it around, that wouldn't be a different stereoisomer. Okay, right, get rid of that. I'm just going to put in those the diamino ligand. Okay, so that's going to be like that, there and there in that one, and in this one is going to be like this. Now we have to think, is there another, right, this one was sorted out, there's only really one like that, but this we have to be careful, because you probably remember when you have got bidentate ligands, you can sometimes get optical isomerism. In other words, you get two mirror images, non-superimposable mirror images, and this thing we've drawn here has got an optical isomer. Imagine that's a mirror, and you could have a reflection of that on this side here. I won't draw it, but that would be another optical isomer. So how many, another stereoisomer, optical isomer. So how many have we got? Well, we've got two optical isomers here. And then we've got this one isomer, which is a cis trans isomer. So the total number is, we've got 3 different stereoisomers. B is the answer. This one, of course, doesn't have an optical isomer. If you know, the mirror image of that, you can superimpose on it. But this one here, you can't. Okay, 14. Which properties are correct for a transition element? Right, now the element has atoms with a partly filled d subshell. That is not true. Okay, it's the definition of a transition element is for something that forms ions with partly filled d shell, not atoms. So the best example to illustrate that would be scandium. Okay, the scandium, the element is 3d1 4s2. So it has got a partly filled d shell when it's an atom, but when it forms a scandium ion, it's got no electrons in the d shell, so and it only forms that ion. So scandium is not considered to be a transition metal because it doesn't form an ion with that. So that's just to illustrate one is actually wrong there. Number 2, do they have more than one oxidation state? Yeah, they always do. And do they form colored ions? They do tend to form colored ions. So 2 and 3 are both correct. So the answer there is C. Okay, so this is the 4 redox system relevant to the hydrogen oxygen fuel cell. Okay, right. So which statement are correct for the alkaline hydrogen oxygen fuel cell? Okay, now the reaction at the positive electrode is, right, so let's just first of all, before we do that, which 2 half equations are relevant into alkaline conditions? Well, that one isn't because you've got H plus ions in it. That's impossible in the alkaline conditions. And that one isn't either because you've got H plus ions in it. So it's only these 2 that we need to worry about. Now the reaction to the positive electrode is not that, because that doesn't happen because you've got H plus ions in, so forget that. You don't even have to worry about whether it's positive electrode. The overall cell reaction is that is always true for the hydrogen oxygen fuel cell. If you want to convince yourself of that, let's have a look. Right, these are the two half equations we want, the ones here, there and there. Now which one is going to go forwards? Well, the most positive one is the one that goes forward, so that's going to go forwards because it's the most positive. It's the best at taking in those electrons. This one is going to go backwards because that's the most negative, best at giving out electrons. Now, if you combine those 2 equations there, you'd have to multiply this one by 2, and if you did that, all of the OH minus signs will cancel out, and you end up with that H2 and O2 going to water. That is correct. The cell potential is 1.23 volts. Well, let's see if it is. Well, the cell potential, E cell, is going to be equal to the most positive one, positive, minus E, the most negative one. So that's going to be 0.4, this one here, minus 0.83. And that is equal to plus 1.23 volts. So that is correct. So 2 and 3 are correct. So C is the answer there. Okay, so that is the end of the multiple choice section. Right, question 16. Humphrey Davy discovered several elements, including sodium, potassium, and so on. Explain which block in the periodic table sodium and magnesium belong to. Well, here we go. They are in this block here, which of course is the S block, because the last orbital to be filled is the S orbital. And in the case of these 3, it's the 3s orbital for sodium and magnesium. So they're in the S block. Just 1 mark answer there. Okay, so here is working out relative atomic mass. Okay, so we're doing it backwards. Okay, so you've got a sample of magnesium consists of 3 isotopes. Okay, and they've given us 2 here, and you've got to determine the relative isotopic mass of the third one. Okay, so first of all, we need to work out, let's call that one, let's call it X. Let's say it's X. We need to work out the relative abundance of X. So the abundance of X is going to be 100 minus the 78.99 minus 10. We've all got to add up to 100, obviously. So that is going to give us 11.01%. Okay. Now, when we're working, how do we work out AR? Well, AR is equal to, you add up the sum of the abundance for each isotope times the mass of each isotope. Right, let's put the numbers in. So we know the AR is 24.305, sorry. Okay, now the abundance of the 24 is that one. Now we're going to do it as a decimal, not as a percentage, so it's 0.7899 multiplied by the mass of that one, 23.985. This is the sum of all those three isotopes, of course. So let's do it for this one, for the 25. That's going to be 0.1, that's the abundance, multiplied by 24.986. And then we're going to do it for X, which is the abundance of X is 11%. So that is going to be 0.1101, and the X is the relative isotopic mass of that one. Right, so if you just simplify all that, you end up with 24.305 is equal to, work out that bit in the blue there, that actually I won't work out all the individual bits, that gives 0.1101x plus 21.4443. I'd leave those numbers in your calculator because it does ask it to 5 significant figures. Right, so if you just solve that for X, you get X there is equal to 25.982, and that is to 5 sig figs, which it asks for. So it's not really a very difficult question. We just got to be careful because a lot of numbers there, a lot of long strings of numbers. Okay, right. Calcium. A student adds an excess of calcium oxide to water in a test tube. In a separate test tube, the student adds an excess of strontium oxide. Write an equation for the reaction of calcium oxide with water. State symbols are not required. Okay, so calcium oxide, it will react with water to form calcium hydroxide. And the reason why it's probably not asking you for state symbols is, of course, calcium hydroxide is, you can't really say aqueous or solid because it's sparingly soluble. And that's related to the next bit here, right? Sparingly soluble, and it's got OH minus ions in it. So it's going to make it quite alkaline, but not really alkaline because it's not going to be pH 14 because it's not completely soluble. So it's going to be about 12 with calcium oxide, I'd say. Now with strontium oxide, you get exactly the same reaction. It forms strontium hydroxide, but that is quite a bit more soluble than calcium. Okay, so you get a higher concentration of OH minus ions, you get a higher pH. So if you put 14 there, that would be fine. I think if you look in the mark scheme, as long as they're both greater than 7, and that this one is greater than the value for calcium, you get the marks. But I think if you did that, you probably get about 12 for the calcium and about 14 for the strontium. Okay, so this is now going on to the Born-Haber cycle. Okay, and it is working at the Born-Haber cycle for potassium oxide. Right, and you've got an incomplete Born-Haber cycle below. And well, first of all, you've got to fill in the boxes, and then later we've got to work out the lattice enthalpy for potassium oxide. Let's do the first bit. So 4 marks, we've got to fill in these boxes here. So, right. So you've got to know how to do a Born-Haber cycle here. So let's see here. We should have in this box here, we should have the elements in the standard state. So that's going to be 2 potassium solid, and you're going to have a half O2 gas. That's the standard. Okay, so here this is going to be delta HF, that arrow going down there. That's delta HF to form the other one. Now what we're doing with this red arrow, we are atomizing the oxygen, yeah, and we haven't done anything to the potassium. So this blue arrow here, what we've got to do, we've got to atomize the potassium. So that's going to go to 2K gas. Atomize that plus O gas. This arrow here, we've done the first ionization of 2 potassiums, and we haven't done anything to the oxygen. This one going down, we've well, you're going to, it's the first one here, it's the electron affinity. You're sticking an electron onto the oxygen, so nothing's happened to the potassium there, so you're going to have 2K plus gas plus O minus gas, and you've got 1 electron left over. And then in the second step here, I'll do it in yellow, what we're doing is sticking another electron onto the oxygen, so that's going to be 2K plus gas plus O2 minus gas, the oxide ion, and that's all of that done here. Right, now calculate the lattice enthalpy of potassium oxide. So we need to put the numbers in here, so let's do that. Right, what have we got here? I'll do these all in, do them in red. Okay, here is the enthalpy of formation, which you look up is minus 363. Here is twice the sorry, you've done the atomization of oxygen, so that's plus 249 there. Here we've done twice the atomization of potassium, so that's 2 times plus 89 for that bit. Here we've done twice the ionization and first ionization energy of potassium, so that's 2 times 419. Right, and on this one, first atomization, so I'll do that in different color. We've got first electron affinity, sorry, you've got minus 141 there, and then here we have got the second electron affinity, we've got plus 790. Okay, so what I like to do here is, the reason, the whole point of drawing a diagram for the Born-Haber, so you don't have to worry too much about the signs. So I'm just going to add up that lot there, all of that, those red numbers. So if you add that up, you get 1628, and I'm not worrying about the sign too much there. So we can see then our lattice enthalpy. What have we got to do? Well, we've got all that red there. We've got 1628, and then we've got to take away 141 there. So let's just write lattice enthalpy. So we've got 1628. We've got to take away 141. It's going down a bit, and then we're going back up, so we're going to add that on there. That's plus 790. Okay, so we do all that, we get a value of that gives us 2277 kilojoules per mole. Now we have to work out the sign. Right, that arrow is going down. Okay, that's lattice enthalpy of formation. When you're going down, that means you've got to have a negative sign. So it's minus 2,277 kilojoules per mole. Yeah, important to get the sign there. Look at the arrow. Arrow's going up, exothermic, so negative values. Arrows going down, exothermic, negative values. Arrows going up, endothermic positive. As I say, I don't worry too much about the signs. Just use the diagram to see, to let you work out what the signs are. Okay, you can construct a similar Born-Haber cycle to potassium oxide for sodium oxide. The first ionization energy of sodium is more endothermic than that potassium. In other words, it's harder to remove an electron from sodium than from potassium. Why? Right, it's because sodium, you are removing it from the 3s orbital, which is closer to the nucleus. And I would say you've got less shielding also. Okay, so it's harder to remove that. Whereas for potassium, converse, you've got 4s, it's coming from the 4s, further away from the nucleus, more shielding, easier to get rid of it. Don't forget, the first ionization energy always decreases as you go down any group in the periodic table, not just group 1. Okay. The lattice entropy of sodium oxide is more exothermic than potassium oxide. Explain why. Right. Okay. Well, it is about the attraction between the positive and negative ions. So the electrostatic attraction between Na plus and O2 minus is stronger than for potassium and O2 minus. Why is that? Well, the reason for it is they've both got the +1 charge, but the sodium ion is smaller. It's smaller than the potassium ion, so we can get closer to the oxide ion, so there is stronger electrostatic attraction. I'd probably use those words in your answer, electrostatic attraction. Okay. Right. Or you could also say, if you want to, I like to explain it that way, you could say that the charge density on the sodium ion is bigger than the potassium ion because the sodium ion is smaller, so you get stronger attraction that way. I think I prefer saying that way. Right, this is a question about buffers now. Question 17. Right. Carbonic acid is a buffer, okay, and it buffers the blood. So let's write down the weak acid which is involved there. We've got H2CO3, carbonic acid, and it's going to lose a proton to form its conjugate base, the bicarbonate, hydrogen carbonate ion, and a proton. Okay, explain in terms of equilibrium how the carbonic acid hydrogen carbonate mixture acts as a buffer, right? And then we've got to calculate this ratio. Let's do the non-quantitative. Let's just do this descriptive bit first. How does this work as a buffer? Well, I would say when you add, if any, what is a buffer solution? Maintains pH, right? So or resist, let's say resists changes to pH. Upon addition of small amounts of H plus ions or OH minus ions. That's the usual definition of a buffer. Right, what would happen if we add H plus ions? So let's say, how will it resist change? Add H plus ions. Well, Le Chatelier tells us that this equilibrium, if you add H plus ions, it's going to try and oppose the change. So add H plus ions, the equilibrium shifts to the left. In other words, the hydrogen carbonate will react with H plus. Let's think if we add OH minus. Right, if you add OH minus, that will react with H plus to form water. So that will lower H plus. So the equilibrium is going to, if you lower H plus, it's going to shift to the right. So as long as you have got some hydrogen carbonate ions, they will dissociate. They will dissociate to form some H plus ions. So you don't get much change. Okay, so that's the descriptive bit done. Let's do the calculation part now. Okay, so, well, we need to think about this equilibrium here. Yeah. Okay, and we need to write down the Ka expression for that. So let's do that. Right, Ka is equal to H plus concentration multiplied by the hydrogen carbonate concentration divided by the concentration of H2CO3. Okay, so we can actually rearrange. Now what this question is asking us to work out this ratio, the ratio of these two concentrations in the blood. Okay, so let's do a bit of a rearrange that equation to get that ratio. So what do we get? We get in black. We get that divided by the concentration of the carbonic acid. That's going to be equal to Ka divided by H plus concentration. Now it gives us the pKa, which is equal to, it told us the pKa of the acid there was 6.38, and it gives us the pH of blood, which is 7.4. Right, so how do we work out the Ka from the pKa? Well, Ka, of course, is equal to, so I'm going to do that here, Ka is equal to 10 to the power of minus pKa, and also H plus concentration is equal to 10 to the power of minus pH. So let's put those numbers in. So we get 10 to the minus 6.38 divided by 10 to the power of minus 7.4. Put those numbers into your calculator and you will get a value of 10.47 is the ratio, approximately equal to 10.5. Okay, so the ratio is, I would say, give it to 3 sig figs, is 10.5. This ratio here, that's what the question is asking you to find out. Right, red blood cells contain hemoglobin. Explain using ligand substitutions how hemoglobin transports oxygen around the body. Okay, well, the hemoglobin contains the heme group, which has a central Fe2 plus ion, okay, and that forms a complex ion. Right, so when the hemoglobin has got no, or let's say, when the hemoglobin, or Hb, binds oxygen, the O2, one of the lone pairs, forms a dative bond to the Fe2 plus ion in the heme complex. Okay, so that's what happens there. Now, when it loses oxygen, when it gives up its oxygen in the tissues, the oxygen ligand is replaced by a water ligand. One of the lone pairs on the oxygen, the water, forms a dative bond to the Fe2 plus. Okay. Right, that's got 2 marks. Now it says, why is carbon monoxide toxic? Okay, so we need to explain there that carbon monoxide has, a minute. Carbon monoxide, okay, has got a lone pair of electrons on the carbon, and that will form a dative bond to the Fe2 plus. That will act as a ligand, and it forms a stronger dative bond than the oxygen does. It means it's harder to break, so it doesn't allow the oxygen to form a dative bond to the central Fe2 plus ion, and so the hemoglobin can't carry oxygen around. So that's why it's poisonous. Okay, so this is about transition metal chromium in aqueous solution. Okay, so before we look at the question, let's just see what's going on here, and then we'll answer the questions. So experiment 1. So you've got this complex here. You've got the hexaqua chromium 3 plus. Okay, now if you add ammonia to that, you form a purple solution, and the purple solution you're going to form is due to this complex Cr NH3. You've replaced all 6 waters with ammonia ligands, and the charge on that is going to be 3 plus. Okay. Experiment 2, that's what's going to happen there. So then if you add sodium hydroxide to this thing here, you're going to get a grey-green precipitate. Now the precipitate formed is actually CrH2O 3OH3. Okay, it's that complex, but I think they just want you to simplify it and write OH 3 times. Okay, so that's what, and that is the grey-green precipitate, that one there. Right, now if you add excess NaOH, what happens is you will replace all of these 3 water ligands here, and you'll end up with a complex ion, which is CrOH6, and that will have a 3 minus charge on it, because you've got a 3 plus on the chromium, and each hydroxide ion is a 1 minus. Step 3, if you add hydrogen peroxide to that, it's an oxidizing agent, all right? And the oxidation number of chromium there is +3, and you're going to oxidize it up to the +6, and you need to know that. Just one thing you need to know. And what is the yellow ion formed? Well, the yellow ion formed is the chromate 6 ion. That's CrO4. That's 2 minus. That's yellow. That's what it is there. Now, if you acidify that, it will turn it into the dichromate ion, and the dichromate ion, I'll just get the color, is orange. Okay, the dichromate ion there. So they've both got a +6 oxidation state there. The yellow one exists in alkaline solution, the orange one, the dichromate, in acidic solution. So let's just use that to answer the questions they've set there. But that's what's going on there in those series of reactions. So we've got redox and we've got ligand exchange. The formula of the complex ion, the purple solution, where we've said that, that's going to be CrNH3 6, and it's going to have a 3 plus charge. An equation for the experiment for the reaction in experiment 2. Okay, so that is when you add excess sodium hydroxide to the precipitate. So we could write that down as chromium hydroxide, and you're going to add so that's been aqueous. Sorry, that's going to be solid, isn't it? We're going to add 3 OH minuses, aqueous, and that is going to give chromium OH 6, and that's going to have a 3 minus charge. If you prefer, and that is going to be in aqueous solution, that's soluble. Okay, so the solid precipitate redissolves. If you want to put in the sodium ions there, obviously it's going to be you probably get away without putting them in. 3 NaOH goes to Na3 chromium OH 6 aqueous. Okay, so you can write it like that as well. Okay, draw a 3D diagram to show the shape of the complex ion formed in experiment 2. So we've got to give through a 3D diagram for this thing here, where it's got 6 ligands, so it's going to be octahedral. So we need to draw that. Right, so we're going to have CR. We've got 2 going back into the plane of the paper, 2 ligands coming out. That's going to be OH, 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 and it's important to show that the oxygen is forming the covalent bond there, so doing it that way around. Then you have what, so those 4 are in the same plane, sticking up, you have 1 OH there, you've got 1 OH there, and we're going to include the charge in the ion, so put a bracket around it and show that it has got a 3- charge. Right, what's the formula of the ion that causes the yellow color? We said, well, that is the chromate 6 ion. And the color of the solution that forms the next, well, that's because we've got the dichromate ion. So the dichromate, when you acidify it, you're going to get that, and that is orange. It doesn't ask you this, I'll just write down the equation for that before I finish up here. So if you get chromate plus acid, we need 2 of those, we're going to get the orange dichromate there and a water molecule. That is the equation there. And the reverse of that would be, right, you've got the dichromate, if you add alkali to that, you end up with the yellow chromate, and you'll form a water molecule there as well. Okay, that's about halfway through the paper, so I'm going to stop there and I'll do the second half in another video.